going to use that equation. Go ahead. Who's reading?
I can read it.
Okay, Sarah, go.
15. To measure the acceleration due to gravity on a distant planet, an astronaut hangs a 0.055 kilogram ball on the end of a wire. The wire has a length of 0.95 meters and a linear density of 1.2 times 10 to the negative 4 kilograms.
Okay. That's linear density, which is mass per length. Okay. Well, and that was the length. All right, go ahead.
Using electronic equipment, the astronaut measures the time for a transverse pulse to travel the length of the wire and obtains a value of 0.016 seconds.
16?
Yes.
Okay.
The mass of the wire is negligible compared to the mass of the ball. Determine the acceleration due to gravity.
We want to know G on this planet. Okay. If you look at the free body diagram, you have mg, and you for the ball, it said the string was negligible mass. Mg for the ball, tension up here, and the ball's just hanging there, so they're equal. So tension has to be equal to mg, doesn't it? And I have an equation up here that has tension in it. If I can solve that for tension, and this is the mass of the ball right here, then I can divide to get G. All right, so I can think of that as mg. I have a number for m over L, I've got that. I want to know tension. I just need to find velocity. How am I going to get velocity of the wave that's created that travels from here to there? How do you get velocity of something? Well, you either do this, but that doesn't look like a good way to do it today because I don't know either one of those, do I? What's the other way to get velocity of something? About the distance divided by the time. You ever heard that equation before, Claire? Yeah. The distance would be the length of the string, we know that, and the time was given as well. So that's 0.95 divided by the time 0.016. And that should give us V. Let me see if I'm on course here. That turns out to be 59.4. 59.4. Oh, did we start that? You did start it, didn't you? Hi, Lily. Hi, Sophia. Do y'all think Sophia's watching this?
Yes.
That is the speed of the wave because it took that much time to go that distance. If you know the speed of the wave, now back to this equation, you've got everything you need. That speed is 59.4. M over L is 1.2 times 10 to the negative fourth. Solve that for tension, and then remember that tension is equal to mg because the ball's not moving, the sum of the forces is 0. So take the tension you found here and divide by the mass, and you've got G. Is that okay without me writing all that on the board? Or see what we did? Anytime you have something hanging, there is tension in the string, and that tension can be thought of as this tension right here. Yes?
Can you just put mg into that problem?
Yeah, that's probably what I would do. For this problem, you can just put mg there, and then just solve it for G. Yeah. Because you know the M. Okay. That's number 15. Number 17 appears to be the next one. Let's go back and put this back as tension. All right, what do you have? Somebody read. Sarah, are you still reading?
Yes.
Number 17.
There's a drawing.
A drawing. What's the drawing look like? Which one is it? That? There's a weight hanging.
Two transverse wave traveling on strings.
There's an attachment here with a wave, and then there's a weight hanging here, right?
And it's 26 newtons.
It's what?
26 newtons.
That's this? Okay, 26 newtons. And over here you've got some kind of wave, is that true? I don't remember what that one looks like. Okay, all right, so we've got a pulley here, and there's a pulley there, and there's a pulley here, I think. And there's a weight here.
And that's 26 newtons.
26 Newton weight, okay.
The linear density of each string is 0.065. The tension is provided by a 26 Newton block that is hanging from the string. Find the speed of the wave in part in the A and
Find the speed of this wave and then find the speed of that wave? Okay. Once again, mg is equal to tension. That's what the tension is. And we know mg is 26. So the tension we know is 26. Just from that. You need to get that. Now, if you know the tension and you know the linear density, you can use those two numbers here to get the speed of this wave. And that, this is number 17 now. Let's see if I have found the speed of this wave. Here's number 17. I find V to be 20 meters per second. And that was that question A?
Yes.
Okay, so question A is just realizing 26 is the tension. They gave you linear density, divide and take the square root. That's question A. Question B is asking for something else. What's it asking for?
the second one. The velocity of the second one.
Oh, okay. For the second one, here, the free body diagram is really the only difference. Here's mg, which we know is 26. Here's the tension. However, there's tension here and there's tension here, isn't there? Now that's all one string, so the tensions would be the same, but there are two forces pulling up. Therefore, each one must be how much? Half of the 26. That must be 13, and this one must be 13. The two ups have to equal the down. The sum of the forces is still 0. Okay? Sum of the forces is 0. So, but the point now is there are two upward forces, one downward force, so these have to each be 13. Now, if the tension here is only 13, you go back to this equation but put 13 in there. And that comes out to be 14 is the answer. So for part B, when you plug in V is equal to the square root of 13 over the linear density, you're going to get that answer to be 14 meters per second. So in both cases, you're just using this equation as can you figure out the difference in the tensions? Okay? Everybody get that? Any questions about that? Nate, any questions? Nope. Let's go to number 19. Okay, go ahead.
Two blocks are connected by a wire that has a mass per unit length of 8.5 times 10 to the negative 4. One block has a mass of 19 kilograms and the other has a mass of 42 kilograms. These blocks are being pulled across a horizontal frictionless floor by a horizontal force P that is applied to the less massive block.
Is there a picture of this?
Mm-hmm.
No? Okay.
You just have to-
So the forces are being pulled by, the masses are being pulled by some force P. Are they, one's
Yeah.
19 and one's 42, are they both being pulled? Like,
They're connected by a wire that has a mass per unit.
okay, so one's 42 and one's 19. I don't know how to draw this exactly, but that's what it sounds like. And there's a wire connecting them, you said? And what do we know about the wire? Anything?
It's linear density.
That's what this was? Okay, good. Go ahead. What
A
next?
transverse wave travels in the wire between the blocks with a speed of 352 meters per second.
200,
352
352 meters per second is the
relative to
velocity
the
of the wire.
wire.
Is that right?
Yeah.
Okay, go ahead.
The mass of the wire is negligible compared to the mass of the blocks. Find the magnitude of P.
Okay, so it's accelerating. Was it accelerating? I don't know. Here, let's see if I have everything down that we know. We know the two masses, we know the speed of the wave in the wire that's connecting them. They're both moving to the right, pulled by a force P. It was frictionless, so they have to be accelerating. There's no backward force to cancel out P. So they are accelerating. And I'm sorry, what was the question? What am I trying to find?
P.
Oh, I'm trying to find P. Okay. The sum of the forces equal MA, and the force, the only horizontal force is P, so it's equal to MA. However, this force would not be P. The tension in this wire here would not be P. It would be this fraction of P, or we could set up its own equation. What's the easiest way to do that? I know it's a fraction of this over the whole, but I guess we could find, we need to find what this tension is so we can increase it by the right amount. That's what we're gonna have to do. All right, we know the speed. Think of a wire here, and V is equal to the square root of tension divided by M over L. And we know the velocity, 352, and we know the M over L to be that number. So we can find the tension in this wire that way. So solve that for Ft. If you know the tension in this wire, then you go back to this thing, where P, here, let's do it this way. T, let's see. The easy way would be just to set up the fraction. I'd like to write it out the way I taught it to you back in the fall. This force, if you isolate that block right there, you would say that tension is the only force acting on it, and it's equal to 42 times A. What is A? I'm having a hard time writing it out, but it's going to be 19 over 51. Hold on. Oh, I should finish. What did I get for tension over here? I got 105. Okay. All right, that's what that is. Now, they're both accelerating at the same rate. So one of them has the tension equal to 42A. I don't guess I ever did that. What am I doing?
Now find A and then add the masses together to get the total force.
I can find A. P minus 105 is equal to 2.5. Anybody else get that?
Yes.
For the 42, it's 105.
Okay.
You're so close.
Divided by 42. Okay. If I put 105 here, because I just found that, and I put this here, I don't know if this is going to help me or not. 105 divided by 42 is 2.5. That's the acceleration of this block, because we know that tension and we know that mass. A has to be 2.5. This is also accelerating at 2.5. So now P is pulling that mass and accelerating it at a rate of 2.5. Okay, so this may not be the easiest way to do it, but now the sum of the forces for the whole system is P to the right and then 105 to the left. Because we just found this tension to be 105, so if I isolate this block, it's got P to the right and 105 to the left, and that's equal to 19A. Seemed like there's an easier way to do it, but this certainly will give me the right answer. And I know A is 2.5. So P minus 105 is equal to 19 times 2.5. And I'm probably off the board there for Lily, but that's what we're doing. Okay, and if you solve that for P, I think it ought to be right. I'm not sure that's the way I did it here. I didn't understand what's on my paper. But the right answer, does that come out to be 153 newtons? That's the right answer. It ought to, I think. And there are probably other ways to do it too. It looks to me like I did it 2 or 3 ways on this sheet of paper in front of me. But
What's the answer?
the new physics is knowing that if we isolate the 42 kilogram, that tension is the only force acting on it, so that tension has to equal ma. So that gives us the acceleration. And then here's the new physics, actually. We just found that the tension, or we solved this for tension because we had velocity and m over L, so we know tension is 105 here. And now we isolate the 19 kilogram block, and there are 2 forces acting on it, P's to the right, 105 to the left. They have to add up to ma. That's what I did. And again, there's probably, you could have set up a ratio, maybe made it easier, but that still works. Okay. All right. Any questions about that? All right. Then I'm looking at number 20. Is that true?
Mm-hmm.
Okay. Number 20, some of you said you got it right, I think. If I recall. All right, read number 20.
A spider hangs from a strand of silk whose radius is 4 times 10 to the negative 6 meters.
Wait. The radius is what?
4 times 10 to the negative 6.
Negative 6? That's the radius of the string? Okay, good.
The density of the silk is 1,300 kilograms per meters cubed.
Kilograms per meter, so that's the linear
Okay.
density?
No, kilograms. The density.
Oh, so it's kilograms per cubic meter?
Here.
Okay, that's the actual density. Go ahead.
When the spider moves, waves travel along the strand of silk at a speed of 280 meters per second. Determine the mass of the spider.
Okay, here's the string. Here's the spider with 8 legs. And we have the radius of the string. We have the density of the string. And we have the speed of the wave. And once again, that's mg, and that's tension. And they're equal. Was the question the mass of the spider? Was that the question?
Mm-hmm.
Okay. So we're trying to find tension because it's equal to mg once again. If you can find tension, it's equal to mg, you can divide by g and get m. All right, so again, if you want to put mg up here into that equation, you can. We've got a velocity, we've got g. We just need to find the linear density from the information they gave us. Linear density is length divided by, it's mass divided by length. And what we know is the density, which is mass divided by volume. But the volume of a string is some fraction times r cubed. What is the volume of a cylinder? It's just length times area, right? So it's pi r squared, no, pi r, length times area. Length times 2 pi times pi r squared. Why doesn't that come out to be right? I wish I had number 20 on a sheet of paper in front of me right now, because I'm struggling over the volume of a cylinder. It is pi r squared L. That's what I said. I don't know why that didn't sound right when I said it. Yeah, it's the area of the circle. I really wish I had a marker that was right. Okay. It's pi r squared times L. That's the volume of the string. What we know is the density of the string, and density is mass divided by volume. And so we know the density to be 1300, and we know I don't know what we know. Density, we know R, okay. And I don't see right on, is there something I didn't write down? 1300 is m over pi r squared L.
Yeah, I think we have to find L first.
Oh, okay. The L's are going to cancel out if you put them up here. Or something cancels out. I have, what I did on my paper I see now is I solved this for m. And 1300 times pi times r squared is 6.53 times 10 to the negative 8 times L, because L is, we don't know what L is. And then I can, if you plug that in over here, you have V is equal to the square root of mg over, for m, I can put 6.53 times 10 to the negative 8 L divided by L, okay, and they go away there. That's just one way to do it. And I have a number for V, so at this point I can solve it. The V is 280. So, yeah, that's the V. That's the mass of the spider. That's 9 point, which is the question, that's 9.8. This is what I came up with for M. And when you put M over L, the L's cancel, and so you can now solve that for mass of the spider. That's not the only way you could have written it out or solved it, but that's one way. Okay. Everybody see what we did? Or you come up with a way of your own to come up with a number. The whole thing, we knew this and this. The whole thing was, can we come up with something for linear density? That's what the problem was in this one. Okay. All right. That answer again is 5.22 times 10 to the negative fourth kilograms. Any other questions on your homework? All right. I realize I'm going to have to spend less time going over homework because we really use up a disproportionate time of our class is used just going over homework, where I'm not teaching you anything. And that's why, I think that's why we get behind. So, and I did that again today, we spent most of our period just going over homework. What I need to do is say, we're gonna take 15 minutes to go over homework. When that's up, we stop. And if you still have questions, then come see me. I'm gonna try to do that in the future so we don't have this issue where we spend the whole time going over homework and now you've got a new set of homework and I haven't taught you how to do it yet. See the issue? Okay. Let's use the time we have left though, rather than go over CYU questions, which always gets bumped to the end of the chapter because we spend too much time going over homework. Rather than that, we're going to teach you what you need to know for this next section. Okay. Your homework tonight is H and I. You want to go ahead and note that. H and I due tomorrow.
What?
H and I.
You mean F and G?
F and G due tomorrow. Oh yeah, I looked at Tuesday, I'm sorry. Thanks for catching me on that. Your homework tonight is F and G. So if you wrote H and I, that's tomorrow night's homework. F and G due tomorrow. Everybody get that changed? I'm sorry, I told you the wrong thing. All right, we are going to now look at finishing up. Oh, we won't really finish it up. We're going to talk about sound waves. Let's see if there's anything I need to teach you before we can do sound waves. I should go back to what I was saying before the prayer. Let's make sure we know what everything means or what it comes from. And we've talked about most of this. The velocity depends on the medium. The frequency depends on the vibrations at the source. How fast, at what rate is my hand going up and down as I shake the spring, for example. And then this is the variable, it depends on the other two. All right, the thing that I mentioned today, well, what determines the amplitude, that is determined by the amount of energy put into those vibrations at the source. Okay, so that also is determined at the source. Whatever is causing the vibrations that create the waves, that amount of energy determines the amplitude. Amplitude is how high it is above equilibrium. So more energy into that one than there was in this one, even though they have about the same wavelength. Wavelength is from here to here, wavelength is from here to here, but that one has a much greater amplitude. So amplitude and wavelength don't really have anything to do with each other. Okay? Amplitude is not anywhere in this equation. All right, this concept there. Then I also want to mention this for a string. If you have a guitar string that's attached at both ends, you have to think a little differently about this equation. Because now the wavelength is locked into that distance. You can't, if it's going to vibrate and resonate and create a sound, which is what you want for guitar string, it's locked into a wave where from here to here is half the wavelength, or from here to there is the whole wavelength. But the wavelength depends on this distance, which you can't change on a guitar. From one end of the string to the other is set. So the wavelength on the guitar string is not really a variable. It's set by the guitar. That's why That's why when you use this equation we were just talking about with a guitar string, you adjust the tension by turning the key at the end of the arm of the guitar, and that changes the frequency of the waves, which changes the frequency of the sound we hear. Now we know that's true. Guitarists tune their guitars that way. Doesn't change the wavelength, it changes the frequency. Even though I told you the frequency depends on the source. And if I'm shaking a spring, that's true. But if you're plucking a guitar string, frequency is directly proportional to velocity because lambda is established by the length of the string. So it's a little different. When I'm shaking a spring, I can give it different wavelengths. But for a guitar string, lambda is set. So it's not going to get different wavelengths. If you change the tension, that will change the velocity. If you change the velocity now, that can't change, it's going to change the frequency. Okay, so that's how when you tighten it up, it goes faster. See, that's a direct proportion. If you tighten the string, the speed of the wave is faster. If the speed is more, frequency is going to be higher. So tightening it up makes it a higher note. Okay? Now really we're talking here about the waves in the string. We're not talking about sound waves yet. So I said it makes a higher note, and that's sound waves, but it's still, the frequency of the wave in the string would be higher. Okay? And that will produce a higher sound note. Okay, that's still about strings, which was really in the last section that we already did homework on. But I want you to know in general, lambda is the variable. It's only not a variable when you have a length of string that's really attached at both ends. Okay. All right, that's that. Now let's talk about sound. Sound waves. Sound waves are longitudinal. I've already told you that. They're not transverse. Sound waves do need a medium. They will not pass through a vacuum. The medium can be air. Then will sound travel through a liquid? Yes.
Yeah.
Will sound travel through a solid?
Yeah.
Yes. You can be on the top floor of a building and tap a pipe in the plumbing in the wall, and the people on the bottom floor hear their pipe. They hear the sound that traveled through the solid pipe. So yes, but it has to be some medium. Sound will not travel through a vacuum. It has to travel through something that has particles that can vibrate, and they vibrate longitudinally. Okay, then we still. Now compression or longitudinal or compressional waves still look like this, where the molecules are compressed, and then over here they're spread apart. We call this compression. That's where the molecules of air, if sound is traveling through air, are pressed together. This area where they're spread farther apart is called rarefaction, just to get some terminology. It's R-A-R-E. Faction. Rarefactions where they're spread apart, compressions where they're close together. But often we still draw waves like this to represent them. It's hard to draw waves like this. They don't look good. It's hard to measure anything. So when they're drawing it like this, they're kind of saying this is the compression, down here is the rarefaction. Just so we can, but all waves behave the same way anyway. They all use the same equations, doesn't matter what kind there are. Yeah. All right, sound waves. The speed of sound in air. Speed of sound in air at about 20 degrees Celsius, which is in this room about, is 343 meters per second. Now, you can always look these up, and there's a chart in your book that gives you the speed of sound. Speed of sound is not the same, it's not a constant like the speed of light. Speed of sound depends on what?
Medium.
The medium, that's what I already told you. All waves, the velocity depends on the medium. And that's true with sound as well. Okay, would sound travel faster, do you think, in cold air or hot air?
Hot air.
Or is it the same?
Hot air.
It's faster in warmer air, that's true. It's something like at 0 degrees Celsius, air is something like 330 something. And again, you can look those numbers up. But it's slower in cold air, it's faster in warm air. Now, what do you think about a liquid? If sound is traveling through water, and sound waves will travel through water, they're still longitudinal waves. Now it's water molecules compressing, and that compression is moved out instead of air molecules. Do you think it's faster or slower in water than it is in air? It's faster. What? Most people don't guess that, but it is. The speed of sound in water, fresh water, pure water, is about 1,480 something meters per second. Again, I'm not interested in so much that you memorize these numbers, because you can always look them up. You do need to know, without looking up, that the speed of sound in a liquid is greater than it is in a gas. The molecules are already closer together. And so compression comes easier. You can think of it that way. What do you think about a solid?
Faster.
It's even faster still. I don't have any numbers in my head for the speed of sound in a solid, but that's even faster than in a liquid. Liquid's even faster than a gas. So the medium really is the thing that determines the speed of any wave. What is it passing through? Okay. So if sound waves are, someone shouts up here, and these represent, here's compression, here's rarefaction, and these waves are moving in all these directions. They're moving out in all directions from a person's voice up there. Those waves hit the water, and some of the energy from those waves pass right into the water. Now, is the wavelength, that's the distance between waves, right? Up here's lambda. Is the wavelength going to be the same down here as it was up there? The answer is no. V equals lambda F. Because new medium, V is going to be much faster. What doesn't change? The frequency, remember, depends on the vibrations at the source. Unless you're dealing with a guitar string that's tied at both ends, which we're not. So frequency doesn't change. That's how high or low the note sounded. So if the velocity increased, the wavelength has to increase as well, because the frequency is the same. So now the wavelengths are going to be greater in here. And it's going to be moving a lot faster. It's the same sound, but it's moving faster and the wavelengths are bigger, the frequency is the same. Okay? All right. I think we're about out of time for today. Your homework is getting into some of these sound waves, and I don't know that I've taught you all you need for your homework, but do your best. And tomorrow I'm going to start this new thing where we set aside this much time for homework, and then after that we move on. I'm going to try to start doing that every day. I'll be a better teacher. Okay. Yeah, turn that off. Goodbye, you guys. Thanks for watching.